In the heart of our everyday experiences lies a world governed by familiar laws. Objects fall, planets orbit, and time marches forward. Yet beneath this macroscopic reality lies a hidden domain, a realm where the rules of classical physics break down and a new set of principles take over. This is the fascinating world of quantum physics, where particles behave like waves, and the very act of observation influences the observed. Join us on a journey to unravel the mysteries of this microscopic world, exploring concepts that challenge our intuition and reshape our understanding of the universe. This is not just an abstract realm of theoretical equations and complex mathematics. Quantum physics has given rise to technologies that define the modern world, from the transistors in our smartphones to the lasers in our CD players. By understanding the fundamental principles governing this strange and wonderful world, we unlock the potential for even more groundbreaking discoveries and innovations in the future. One of the most fundamental concepts in quantum physics is wave-particle duality. This principle states that particles, such as electrons and photons, can exhibit both wave-like and particle-like behavior. This duality challenges our classical intuition, where objects are neatly categorized as either waves or particles. Imagine a beam of light. We know that light can act as a wave, diffracting through narrow slits and creating interference patterns. But light can also act as a particle, carrying discrete packets of energy called photons. This duality is not limited to light. Electrons, the building blocks of atoms, also exhibit this wave-particle behavior. The famous double-slit experiment beautifully demonstrates this concept. When electrons are fired at a barrier with two slits, they don't just pass through one slit or the other as classical physics would predict. Instead, they create an interference pattern on the screen behind, as if each electron were a wave passing through both slits simultaneously. This experiment highlights the counterintuitive nature of the quantum world, where particles can exist in multiple states at once. Another mind-boggling concept in quantum physics is superposition. In the quantum world, particles do not exist in definite states like on or off, but rather in a probabilistic haze of multiple states simultaneously. This means a particle can be in multiple places or have multiple properties at the same time until we measure it. Erwin Schrödinger, one of the pioneers of quantum mechanics, illustrated this concept with his famous thought experiment involving a cat. Imagine a cat sealed inside a box with a device that has a 50% chance of releasing a lethal poison. Until we open the box, the cat is in a superposition of states, both alive and dead. The act of observation collapses the superposition, forcing the cat into one definite state or the other. This doesn't mean the cat was always in that state, it's the act of measurement that forces the universe to choose one outcome. Schrödinger's cat experiment, while hypothetical, highlights the profound implications of superposition, suggesting that reality is not as fixed and absolute as we might perceive. Quantum entanglement is perhaps the most bizarre and counterintuitive concept in quantum physics. It describes a phenomenon where two or more particles become linked, even over vast distances. When the state of one entangled particle is measured, the state of its entangled partner instantly changes, regardless of the distance separating them. Imagine two entangled particles, one sent to Alice and the other to Bob, millions of light-years apart. If Alice measures her particle's spin and finds it to be up, she instantly knows that Bob's particle will have a spin of down upon measurement, even though there's no time for information to travel between them at the speed of light. This spooky action at a distance, as Einstein famously called it, challenges our understanding of causality and locality. It suggests that there are deeper connections in the universe than classical physics can explain. Adding to the strangeness of the quantum world is the uncertainty principle, formulated by Werner Heisenberg. This principle states that there are fundamental limits to what we can know about a particle's properties simultaneously. For example, the more precisely we measure a particle's position, the less we can know about its momentum, and vice versa. This isn't a limitation of our measuring devices, but a fundamental property of the universe. The uncertainty principle doesn't mean the universe is inherently unknowable. Instead, it highlights the probabilistic nature of the quantum world, where we can only predict the likelihood of certain outcomes rather than knowing them with absolute certainty. Quantum physics, despite its mind-bending concepts, is not just a theoretical curiosity. It has led to revolutionary technologies that shape our world. Transistors, lasers, and magnetic resonance imaging, MRI, all rely on the principles of quantum mechanics. The future holds even more potential with quantum computing, promising to revolutionize fields like medicine, materials science, and artificial intelligence. As we delve deeper into the quantum realm, we continue to uncover new mysteries and challenge our understanding of reality. Quantum physics is a testament to the power of human curiosity and our relentless pursuit to unravel the secrets of the universe, no matter how strange and counterintuitive they may seem.